Hi, my name is Haley Anderson. I'm a senior computer science major at Chapman University. I am going to be doing this project along with my teammates for our 370 class, Introduction to Deep Learning.
Hello everyone, I'm Kolby Ramirez. I am a senior at Chapman University with a data analytics major.
Hi, my name is Brady Hoskins, and I'm a senior computer science major at Chapman University.
Today, we'll be learning about recurrent neural networks, more commonly known as RNNs. An RNN is a specific kind of neural network. If you don't know anything about neural networks or deep learning, I suggest you watch a tutorial video on these topics before you continue with this video. Let's begin with an anecdote on the importance and innovation of an RNN. I think we all remember a time when we were trying to finish a Spanish or other language homework assignment last minute and hopped onto Google Translate to try to find a quick answer. Back in 2010, Google Translate would simply translate a sentence word by word. The gender of the subject and whether it was plural would not be factored in at all, and often the sentence used the incorrect word for the colloquial setting. Basically, it provided a very grammatically incorrect sentence. But now, with the help of recurrent neural networks, these services have become exponentially more accurate. These days, Google Translate gives you an actual sentence with properly conjugated and gendered verbs. Facebook translation services are also quite accurate. Sometimes my friends' statuses are automatically translate, and I can't even tell until I notice the translated note at the bottom. The topics we're going to be covering today are the history of a recurrent neural network, a description along with the description of a long short-term memory and attention. We will also be discussing implementation, problems with standard RNNs, use cases, and how RNNs compare to other models. First, we'll start with the history. So, the recurrent neural network, commonly known as an RNN, was first described in 1972, but popularized in 1982 by John Hopfield, who created the Hopfield network. A Hopfield network was touted as a model for human memory through the ability to look at memory vectors. Hopfield networks were revolutionary as they were guaranteed to converge to a local minimum. Unfortunately, Hopfield networks have a tendency to converge on the wrong local minimum. Hopfield networks are an RNN where all the connections are symmetric and require a stationary input. Because of this, they are not a general RNN and seen as a specific case of an RNN. Later, RNNs as we know them were created by David Rumenthal in 1986. David Rumenthal 1942 to 2011, was an American psychologist who was instrumental in various discoveries and contributions in many scientific fields, especially psychology, deep learning, and neural networks. He grew up in South Dakota with his parents. He received BAs in psychology and mathematics from the University of South Dakota in 1963. He then went on to receive his PhD in mathematical psychology from Stanford University in 1967. He was a professor at the University of California, San Diego, and Stanford University during his career. During his career, he received awards from the National Academy of Sciences in 1991, a MacArthur Fellowship in 1987, the Warren Medal of the Society of Experimental Psychologists in 1993, the American Psychiatric Association's Distinguished Scientific Contribution Award in 1996, and the University of Louisville Gramarye Award in Psychology in 2002. He passed away in 2011 after a battle with the neurodegenerative disease Pick's disease, which is more commonly referred to as frontotemporal lobe dementia. Long short-term memory is a form of RNN that was created in 1997 by Sepp Hostringer and Jürgen Schmidhuber. By introducing constant error carousel (CEC) units, LSTM deals with the exploding and vanishing gradient problems. The initial version of the LSTM block included cells, inputs, and output gates. In 1999, the forget gate was added. Other changes have been made since then as LSTMs grew in popularity. LSTMs are now being used in 4.5 billion Facebook automatic translations per day, as well as in services for other major companies. Sepp Hostinger is a German computer scientist who was born in 1967. He has many contributions to the scientific community, a list of which are long short-term memory, LSTMs, deep learning and learning representations, reinforcement learning, drug discovery, target prediction and toxicology, biclustering, support vector machines, feature selection, genetics, next-generation sequencing, and microarray preprocessing and summarization. He is currently leading the Institute for Machine Learning at the Johannes Kepler University of Linz. Jürgen Schmidhuber is a German computer scientist who was born in 1963. Sepp was a student of his at Technische Universität München. After teaching at the University of München, he now teaches at the University of Civinvera Italiana in Lugano, Switzerland. He is sometimes referred to as the father of AI. He is a co-director of the Dalle Mole Institute for Artificial Intelligence Research. He has formed several successful artificial intelligence companies such as Niacin.
Traditional neural networks struggle with retaining information from its past events. RNNs address this issue by passing information from one of its states to its next. Looking at the diagram to the right, this displays a chunk of a recurrent neural network A. This RNN receives XT as input data. It then produces an output, HT. The loop back into itself shows this network passing information to its future states. Because of this structure, you can think of an RNN as multiple copies of the same network alongside each other instead of each state passing information back into itself. It would be passing information to its next state, thus allowing it to remember features from its past states. One of the appeals of RNNs is the idea that they might be able to connect previous information to the present task, such as using the previous video frames might inform the understanding of the present frame. In cases where the gap between the relevant information and the place that it's needed is small, RNNs can learn to use the past information. In theory, it's possible to train RNNs to remember important parts of the sequence that appear early on. However, in practice, when the gap gets large, the RNN is no longer able to learn to connect the relevant information to the place it's needed. Luckily, the LSTM was invented to help combat this problem. The diagram to the right is the basic LSTM structure that we will go more into depth later on in this presentation. RNNs are used to solve two main types of problems: non-sequential and sequential problems. Non-sequential problems are problems that do not rely on historical information. For example, image classification problems would fall into this category. The other type of problem that RNNs encounter are sequential problems. These types of problems are history-dependent problems. They rely on information that has already been passed into the neural network. For example, speech recognition and speech translation. Humans would naturally know the next word in this sequence. I am from France. I enjoy crepes, and I speak French. The problem with long-term dependency that I mentioned earlier can really rear its head in this example. If the gap between France and French becomes too large, it can be very difficult for the RNN to make this connection. This image shows the four main types of sequential tasks that RNNs are used to solve. One-to-one models take one word or one image in and classify it into one class. One-to-many models take one word or one image and classify it into multiple classes. Many-to-many models take multiple words or images and classify them into multiple different classes. Many-to-one models take multiple words or images and classify them into one single class.
All right, so now let's talk about some of the different problems with a recurrent neural network. So we know that some of the problems with it are things like vanishing gradient descent and exploding gradient descent. But before we talk more about what those problems exactly are, let's talk about some of the history behind gradient descent, or the person that found vanishing gradient problem and the exploding gradient problem. So the first person to discover this issue was someone that contributed greatly into the RNN and LSTM today. So that is Sepp Joseph Rockenreiter in 1991. So he was the first to discover the issue. Next, we had Yoshua Bengio, who was the second to discover this issue in 1994. So 3 years later. So he was also another person that helped contribute a lot to the space of deep learning and RNNs in particular. So next, like we said, the problems with recurrent neural networks are gradient descent. So before we could talk about it, let's talk about what gradient descent algorithm actually is. So the gradient descent algorithm is we talked about it before and we looked at it with other models, but it finds the global minimum of the cost function that is needed to be optimal to set up your network, right? So normally how regular gradient descent works is that it travels through the neural network from the input neurons to the output neurons. And the weight of the error is calculated and then propagated back through the network to then update the weights. So it works similarly here with recurrent neural networks, but that first the information travels through time in RNNs. That's something that's very important, that it travels through time, which means that information from previous time points are used as information to the next time point as well. So, and then secondly, you can calculate the cost function of your error at each time point. So now that you have a basic idea of what we have here, let's go on with some of the different or specifically describing the specific issues with it. All right, so we have the vanishing gradient descent problem now. So if you look at this image below, basically we have a layout of how a recurrent neural network is laid out. So you have information that's getting passed through time that moves to the right and goes forward, and then you need to backpropagate now. So you have your inputs, you have your weight updates, and then you have your desired outputs. So let's focus on specifically one error term, or it is denoted in this image as epsilon t. So you've calculated the cost function, et, and now you want to backpropagate your cost function through the network because you need to update your weights. So essentially, every single neuron that participated in the calculation of your output should have its weight updated in order to minimize the error. And the thing with RNNs is that it's not the neurons directly below the output layer that contributed, but all the neurons far back in time. So you need to backpropagate all the way through time to these neurons or with these neurons. And the problem relates to updating the in the image. If you look, you see WREC, or weight reoccurring. So the weight that is used to connect the hidden layers to themselves in an unrolled, which are the weights used to connect the hidden layers to themselves in an unrolled temporal loop. So, for instance, to get from xt minus 3 to xt minus 2, we need to multiply xt minus 3 by the weight reoccurring. So then to get from xt minus 2 to xt minus 1, we again need to multiply, and that's the key word, multiply xt minus 2 by the rec, or the weight reoccurring. So we multiply with the same exact weight multiple times. And this is where the problem arises, because when you multiply something by a small number, then your value decreases very, very quickly. And as you know, that the weights are assigned, the weights that are assigned at the start of the neural network are random values, which are close to 0, and from there, the network trains it up, right? But when you start weight reoccurring super, super close to 0 and multiply xt minus 1, xt minus 2, xt minus 3 by this value, and so on and so forth, however many neurons you have, your gradient becomes less and less with each multiplication. So now let's talk about the exploding gradient problem that we have here. So before we talked about vanishing, now it's exploding. So, I mean, it's the only difference between exploding and vanishing gradient is that, it's kind of just like how it sounds. If you have a high gradient now, it will explode, and, you won't be able to get very accurate results from it, because if you start with your neural network a weight reoccurring that is very high, then you keep multiplying it by each neuron or each time step that you have, then the value will just exponentially continue to grow with each neuron. So that it's the exact opposite of the vanishing gradient problem. Instead of you starting out with a weight that is small, now, which is the vanishing gradient problem, you now have a weight that is extremely high and then continually gets higher, which is the exploding gradient problems. So now that we talked about the different issues with the current normal standard vanilla recurring neural network, there are other solutions to solve or alleviate this issue. So now that we talked about the problems with RNNs, let's talk about some of the solutions with it. In the last slide, we talked about exploding gradient descent. So let's see what we could do to try to alleviate or solve the problem. So one of the things that we could do is something called truncated backpropagation, which basically just stops backpropagating. You stop backpropagating after a certain time, a certain point, which is not usually optimal because not all the weights get updated then, and then you won't get as accurate results. So yes, another thing that you could potentially do is penalize or artificially reduce gradient. And then finally, another thing that you could do is gradient clipping, which basically means that you put a maximum limit on a certain gradient. So the value of the gradient can be higher than this number. And that helps solves the exploding gradient problem. In the case for vanishing gradient problem, there are three things that you could do. So you could initialize weights so that the potential vanishing gradient is minimized. You could have eco-state networks that are designed to solve the vanishing gradient problem. And then finally, you could have a long short-term memory network, or an LSTM model, which we'll be going back with, or which we'll be talking about in the next slide. But these LSTMs are normally considered the go-to network when you implement a recurrent neural network. So let's get right to it and explaining how or what is a LSTM model.
The history of the long short-term memory unit, colloquially referred to as an LSTM, was discussed earlier in this lecture. Now we'll get into the specifics of how an LSTM works. An LSTM is a unique RNN architecture. What distinguishes an LSTM from other RNN architectures is its ability to examine the context of an input in the model. In theory, a non-LSTM RNN can also keep track of a context of an input, no matter how long-term the information is. But in practice, when using backpropagation through a non-LSTM RNN, the gradient can become extremely volatile and either vanish to zero or explode to infinity, and the information can be too far back in the sequence to be considered by the RNN. LSTMs are specifically designed to avoid the problem of long-term dependencies. They have the ability to fix this and the problem of the vanishing and exploding gradients by allowing the gradient to flow through the RNN unchanged. This ability to identify the context of an input in LSTMs is especially useful to sequential inputs such as language processing. In order to do this, an LSTM employs feedback connections. To do this, it uses multiple parts. An LSTM consists of a cell with three gates: the input gate, output gate, and forget gate. These gates work together to sustain information over time and control the information that flows through the model. This is where the concepts of short-term memory and long-term memory combine. Some information will pass through the cell untouched, the long-term memory, and other information will be changed and updated before being passed along, which is the element of short-term memory. A standard RNN has a similar but much simpler structure than an LSTM. It does not have gates and only a single TAN layer. As you can see in this design, there are many pieces to the design of an LSTM. A standard RNN would only have this single TAN layer. The entire image would be the previous H subscript T minus 1 and X subscript T be sent through the TAN layer and continue on in the process. TAN layers push input values to be between -1 and 1. The cell as a whole is responsible for passing the information of the previous state along in the input sequence. As there are only a few small linear interactions, it is very easy for the previous state information to remain unchanged as it flows through an LSTM. But this cell state can optionally be updated by the gates in an LSTM. All the gates are made up by a sigmoid neural network and a pointwise multiplication operation such as addition. the sigmoid function returns a 1 or 0, meaning that either all of the calculated information will be added to the cell state or none of it will be. We will now go into the specifics of each of these gates and how they come together to solve the problem of the volatile gradient. There will be math on these slides, but don't be scared away by it because the concepts actually make a lot of sense. The first piece of the cell is the forget gate. This gate decides which information from the cell state will be dropped and which information will be kept. The sigmoid function will assign each previous state a 1 or a 0 to be kept or to be forgotten. An example of this cutoff would be that the gender of the current subject of the sentence would be kept so that any pronouns can be accurately gendered. But once a new subject is found, information about the previous subject could be left out and not considered at this time. The next gate is the input gate. This step helps to decide which new information is going to be stored in the cell state. It does this in 2 steps. The first is a sigmoid function on the input which decides which values will be updated. The second step is the tan layer that creates a vector of new values. Together, this creates a list of new candidate values that have been scaled by which values need to be updated. Next, we will add these changes to the cell state. In the first gate, the forget gate, we will remove pieces of information that are no longer needed. The second gate, the input gate, will replace this removed information with new information that is relevant to our current subject. An example of this step would be that when the new subject is introduced, we would forget the old subject's gender and remember the new subject's gender instead. Finally, we come to the output gate. This is a gate that decides what is actually given out. This returns a filtered version of the cell state. We encounter another sigmoid function to choose the pieces of the cell state to output. We then put the cell state through a tan layer and multiply it by the sigmoid gate so that we only return the pieces deemed important, aka the values given a 1 by the sigmoid function. An example of this is if you see a subject, returning whether it is plural or not so that a following verb can be in the correct tense. And this is how an LSTM works. LSTMs work incredibly well for natural language processing, both written and speech, and have been shown to succeed in a variety of commercial settings. Some important ones to point out are in Google's Android translation service and Facebook's translation service. Now we will discuss a specific kind of LSTM, the gated recurrent unit, which is shortened to GRU. The GRU was developed by Kyung Yun Cho in 2014. It aimed to definitively solve the problem of the vanishing gradient. Once again, ignore the math for now. The GRU combines the forget gate and input gates of the LSTM into a single update gate, as is seen in this diagram. It also merges the cell state and the hidden state. Because of this, a GRU only has 2 gates, the update gate and reset gate. The update gate uses a sigmoid function to help the model determine how much of the past information from previous time steps needs to be passed along to the future. The reset gate uses a sigmoid function as well to help the model determine how much of the past information to forget. It then uses a tan function to combine the results of these 2 steps. It then does an element-wise multiplication of this result with the new input information. The sum is then returned. The gated recurrent unit has been growing very popular as of late. Additionally, the website listed in the reference section for both LSTMs and GRUs are fantastic resources for understanding LSTMs and GRUs respectively, and I highly recommend looking at them if you are looking for further clarification. The main difference between a GRU and an LSTM is that a GRU has 2 gates, the reset and update gates, but an LSTM has 3 gates, the input gate, the output gate, and the forget gate. The GRU combines the input and forget gates into a single gate, the reset gate. So, if a GRU has fewer gates than an LSTM, why would you want to use it? While a GRU is a specific kind of LSTM, so they both focus on solving the problem of the vanishing gradient, they have different main use cases. For instance, a GRU does not have a hidden memory state. Instead, the memory is exposed to the working of the cell. This can be helpful for many problems. Because of the one less gate, the GRUs have fewer calculations to make. GRUs therefore need to update fewer training parameters. This makes GRUs faster and less memory intensive than the standard LSTM. But because of having fewer training parameters, the GRU can be less accurate, and they don't do as well on longer sequences. As a GRU is a much newer addition to the neural networks family, it hasn't gained as much recognition as the original LSTM. In some cases, such as inputs with very long sequences, or problems where the exact accuracy is of critical importance, an LSTM is the better bet. But there are many problems that could be just as easily satisfied by using the more computationally effective structure of a GRU. And now we're going to talk about the mechanism of attention. The attention mechanism was originally created to support longer sequences in RNNs. It was observed that longer sequences led to drastic performance degradation. It was an imitation of human sight, which can see all of the context but only needs to focus on relevant words. Developed to ensure that earlier inputs in the sequence are not forgotten by the time the end of the sequence is reached. It makes sure that the intermediate steps of the input are taken into account and can give certain words more attention than others when predicting output, hence its name, attention. The types of attention are generalized attention, additive attention, multiplicative attention, and self-attention. Generalized attention uses the dot product method. In this presentation, we will also discuss the key value method.
There are many ways for RNNs to select the most important attention scores. Two of the more prominent styles are soft and hard attention. Hard attention is the process of calculating the attention scores for all states, then selecting the hidden state that has the highest attention. One common way of selecting the highest attention score is using a function called argmax. The argmax function simply returns the index with the highest value in an array. This is problematic for RNNs because this function is non-differentiable and not able to be backpropagated through, thus making training for your RNN very difficult. Soft attention is the process of calculating the attention scores for all hidden states, then taking a weighted average of the attention scores. This image shows the dimensions that the weight matrices need to be for each of the types of attention. You can see that the conditions that are set on these weight matrices, and you can also see the formulas EI and how to calculate each type of attention. One type of attention is called additive attention. This type of attention is implemented by making a linear combination of your encoder and decoder states. If you look at the image below, this shows a formula for how to calculate an attention score using the additive method. VA and WA are both learned attention parameters. Additionally, UA and WA can be used to learn separate transformations for your two inputs. Typically, additive attention methods will perform about the same as multiplicative attention methods. However, when the dimensions for your data become larger, additive will usually outperform multiplicative attention. The next type of attention we're going to talk about is multiplicative attention. Multiplicative attention reduces encoder states, your HI input, and decoder states, SJ input, into attention scores. It does this by applying simple matrix multiplication. You can see that in the image below. The performance of multiplicative and additive functions are similar in complexity, but the multiplicative function is faster and more space efficient. Multiplicative attention performs similar to additive attention when there's a smaller dimensionality of the decoder states. The next type of attention we will talk about is self-attention. Self-attention differs from other attention models primarily in what it compares its weight matrix to. Other attention models typically compare their weights to a target vector. However, self-attention models compare their weights to previous hidden nodes, or previous parts of the input sequence. This helps us make correlation matrices that show the dependency each word in the input sequence has with other words in that same input sequence. Self-attention models allow us to ignore the distance between relevant words in the input sequence, which traditional RNNs struggle with. This enables us to more accurately learn the structure of input sequences. In language translation tasks, this will help make more accurate translations, especially when looking at the syntax of the sentence. Key value attention is a recent attention variant that separates form from function by keeping separate vectors for the attention calculation. Each source sequence that is passed into the encoder is split into two hidden states, H forward and H backwards. These hidden states are then decomposed into two respective parts, a key and a value. These keys are used for calculating the attention distribution using additive attention methods. In this next part, we are going to compare several of the different types of attention methods. The first comparison we will make is between soft and hard attention. Soft attention models are usually smooth and differentiable, making it very easy to train these models, whereas hard attention models are non-differentiable and require much more complicated techniques just to train the models. Soft attention approaches place their weights softly over all patches in your source input, where hard approaches select only one patch in the source to focus on at a time. Next, we are going to compare self, additive, and multiplicative attention. Additive and multiplicative attention calculate attention scores at every step taken by the decoder. They both then compare the weights to a target vector. In general, the performance of multiplicative and additive attention functions are similar, but the multiplicative function is much more computationally inexpensive. Self-attention also calculates attention scores at every step taken by the decoder. However, self-attention models compare the weights to the input sequence they just saw, showing the relationships within a sequence. Additive and multiplicative functions compare their weights to a target sequence. Let's take a look at an example. Look at this black box to the right. This black box represents a recurrent neural network constructed with an encoder-decoder structure. There are two inputs going into the network. SJ being the current state the decoder is in, and HI being the set of encoder states. If you sum up the attention weights, they add up to 1. These weights are normalized, which means that the list of floating point numbers represent the probability distribution of attention across the encoder states. What can we do with that? If the weights are normalized, we can combine the states together by taking a weighted sum of all the encoder states. This means for each decoder step, we get a new set of attention weights, leading to a new weighted combination of encoder states at every step. The set of floats or attention weights tells the current decoder state how important the corresponding encoder state is. If we were looking at a sequence of words, these weights would tell the decoder which word in the sequence has the most effect on the next word in the sequence. These weights would get recalculated at every step. If we wanted to use a hard attention method of selecting the most important word in the sequence at that time, we would simply choose the word with the highest attention weight. In this case, it would be the fourth word in the sequence with a score of 0.48.
So now we're going to talk about an example of an implementation of a RNN. So let's just go over some of the topics that we'll be talking about in implementing an RNN. So we'll go over the difference between sequential and functional APIs. Then we'll be going over the different libraries needed to build a RNN. We'll be talking about the data that we'll be going over, and then we'll go over like the exact implementation of how to do it in Python. So let's go ahead and go right to it. Alright, so the first topic that we are going to go over is the difference between sequential and functional APIs when building a model in general. So there are two different ways to build models in Keras. So one way is the using the sequential API, and the other is using the functional API in Keras. So what's the difference between them? So first off, the sequential API is just like it sounds. So when you create a layer, or when you create that model, you're doing it layer by layer. And even though sequential model sounds like the more, I guess, easier way to understand, because you build your model layer by layer, it is limited in the sense that it doesn't allow you to create models that share layers or have multiple inputs and outputs. Alternatively, we have the functional API in Keras. So this allows you to create models that have, I guess, more flexibility in the sense that you could easily define your models where layers connect to more than just the previous and next layers. So in fact, you could connect layers to literally any other layer in the model. So as a result, creating complex networks, or you're able to create complex networks such as the size mean network and the residual networks. So if you look at the image on the slide, this is just a very, very simple example of how to implement a size means network, which is a functional API network. And in the sense that size means network is basically it's a neural network that uses the same weights while working in tandem on two different input vectors to compute comparable output vectors. So like I said, this is a functional API because you're able to have two different inputs, unlike the sequential model. And yeah, so let's move on to some of the different coding examples, or how it would look in code. Yeah. Alright, so let's go over the sequential coding example, I guess. So again, the sequential model API, you create a model doing it layer by layer. So in the example, you set model equal to sequential, which is basically your sequential object, and then you do model.add. In this case, we added two different dense layers with two different inputs, one with input of 2, and with 2 nodes and input dimension of 1. This is just a simple example, but you get this idea of if you want to build a very dense network, you would just do model.add whatever you want to add. In this case, we added 2 dense layers. So as you can see, it's a not very straightforward model. You can't have multiple different input sources. You can't produce multiple output dimensions or destinations, and you can't reuse layers in this case using the sequential models. So it's great for developing deep learning models in most situations, but there's a lot of different limitations to it as well. So let's go over to the functional models. So let's talk about the functional coding API. So again, the functional API provides a more flexible way for defining models. Specifically, it allows you to define multiple input and output models as well as models that share layers. So let's look at the example. So you define the input. In this case, we're going to define the input as visible, the word visible, and then we connect the dense layer to the input visible, and then we label it as hidden, and then we then have model, the word model, that specifies the input and output of the models using the inputs and outputs parameter. So this is just an example of a very simple example of how to manage or create the functional API coding example. All right, so let's go ahead and move on to the different libraries that we need, and then we'll go over specifically an example of how to implement RNN.
Throughout our implementation of an RNN, we mostly use methods found within the Keras API. If we weren't using Keras, then our methods came from within NumPy. For our RNN implementation, we chose to use the sequential API, meaning we would build the network up one layer at a time. The layers we used are as follows. First, we used an embedding layer, which maps each input word to a 100-dimensional vector. The embedding layer can use pre-trained weights, which we supply in the weights parameter. Trainable can be set to false if we don't want to update the embeddings. The next layer we used was a masking layer. The masking layer is used to mask any words that do not have a pre-trained embedding, which will be represented as all zeros. This layer should not be used when training the embeddings. The heart of a network is the LSTM. We chose to combine our LSTM with dropout. This was to help prevent overfitting. Since we are only using the one LSTM layer, it does not return sequences. If we were to use 2 or more layers, we would have to make sure to return our sequences. We then used a fully connected dense layer with a ReLU activation. This adds additional representational capacity to the network. We then used a dropout layer to further prevent overfitting of the training data. And finally, we used a dense, fully connected output layer. This produces a probability for every word in the vocab using the softmax function. We then compiled our model with the Atom optimizer and trained using the categorical cross-entropy loss function. During training, the network will try to minimize the log loss by adjusting the trainable parameters, or the weights. There are two main steps for preparing our data. The first is to remove punctuation and split strings into individual words. The second is to convert the individual words to integers. The tokenizer has removed all punctuation and converted all the words to lowercase. If we use these settings, then the neural network will not learn proper English. We can adjust this by changing the filters to the tokenizer to not remove punctuation. We can use the IDX word attribute of the trained tokenizer to figure out what each of these tokens mean. We got our data for this implementation from the USPTO patents view. After we have imported all of our data, the next step is to create a supervised machine learning problem with which to train the network. In our case, we want our network to generate the next word in the sequence. The number of words to put in the training set is left as a parameter. We'll set ours to 50, which means we give our network 50 words and train it to predict the 51st. Other ways of training the network would be to have it predict the next word at each point in the sequence. For example, make a prediction for each input word rather than once for the entire sequence. Or we could have trained the model using individual characters. We use the first 50 words as features, with the 51st as the label. Then we use words 2 through 51 as features and predict the 52nd, and we continue with this pattern. This gives us significantly more training data, which is beneficial because the performance of the network is proportional to the amount of data that it sees during training. The features end up with a shape of 296,866 by 50, which means we have almost 300,000 sequences each with 50 tokens. We are using the Keras sequential API to build our network. Our first layer, the embedding layer, maps each input word to a 100-dimensional vector. Our next layer, the masking layer, is used to mask any words that do not have a pre-trained embedding, which we will represent with all zeros. I will talk about embeddings in a little bit. The next layer is the LSTM. We utilize the dropout within this layer to help our network to not overfit. The next layer is a fully connected dense layer using the activation function ReLU. Then we added an additional dropout layer to further help our network to not overfit. And our last layer is another fully connected dense layer, except this time we use the activation function softmax to generate the probability for every word in the vocab. Embeddings are learned, which means the representations apply specifically to one task. When using pre-trained embeddings, like we are, We hope the task the embeddings were learned on is close enough to our task at hand so the embeddings are meaningful. If these embeddings were trained on tweets, we might not expect them to work well. But since they were trained on Wikipedia data, they should be generally applicable to a large range of language processing tasks. With the training and validation data prepared, the network built, and the embeddings loaded, we are almost ready for our model to learn how to write patent abstracts. Some best practices for training your network are to use model checkpoint and early stopping. Model checkpoint saves the best model, measured by your validation loss, on your disk for later use. Checkpoint essentially allows us to pick up where we left off if our training was disrupted several epochs in. Early stopping halts training when validation loss is no longer decreasing. Early stopping is an extra measure to make sure we are not overfitting our model to the training data. It also saves us time because it will stop training if it is no longer improving. Overall, the model using pre-trained word embeddings achieved a validation accuracy of 23.9%. This is pretty good considering a naive guess of the most common word, the, yields an accuracy of around 8%. Convolutional neural networks do not perform well when the input data is interdependent in a sequential pattern because they have no way of storing correlated information. If we run multiple inputs through a CNN, none of the outputs would have any bias from the previous inputs. Depending on the scenario, we would need the bias from the previous outputs to produce an appropriate output at the current step. This is why we use RNNs. An example of the above would be text translation. Although you could independently translate each word, it would not capture the true meaning of the sentence. You need to have information from the past outputs to generate the appropriate tense of each of the words. Some additional uses for RNNs are text generation, translation, speech recognition, generating image descriptions, and video tagging.
All right, so this next slide, we'll be talking about how RNNs compare to other models. So specifically, we're going to look at RNNs versus CNNs. So we'll be looking at things like how they operate or function, both RNN and CNN, and the different applications of these models and when they're useful. So let's move on. So let's get back into reminders of the architecture of RNN after the little detour that we had with the attentions and different use cases and implementation of it. So, reminder that the RNN, it uses a similar architecture to a traditional neural network. The difference is that it introduces the concept of memory, and it exists in the form of different types of links. So, unlike a feed-forward neural network, the outputs of some layers are fed back into the inputs of a previous layer. So, this addition allows us for analysis of sequential data, which is something that the traditional neural network is incapable of. Also, traditional neural networks are limited to a fixed length input, where RNN has no restrictions. And this inclusion of links between layers in the reverse direction allows for feedback loops, which are then used to help learn concepts based on context. So in terms of what this can do for deep learning application, it depends very much on the requirements and the data. Also, a recurrent neural network is used for time series data that contains repeated patterns. So the RNN is able to recognize and take advantage of those time-related contexts. So this is accomplished by applying more weights to patterns where the previous and following tokens are recognized as opposed to being evaluated in isolation. So for example, consider that we have a system that is capable of learning to recognize spoken language. So such a system would greatly benefit by taking into account recently spoken words to predict the next sentence. One of the most popular frameworks with recurrent neural networks is an LSTM, which is capable of learning long-term relationships. And also there are different types of varieties of recurrent neural networks that also typically depend on a specific task. So there are 4 types that we stated earlier. So we have one-to-one sequence, one-to-many, many-to-one, and many-to-many. And then to understand which of these are suited for a particular job, we need to look at how or when you apply RNNs or versus CNNs, and which ones have, I guess, an advantage, and which ones are effective. But let's get right into the applications of a recurrent neural network. So, some of the things that, or some different applications of a recurrent neural network are image classification. So basically that's where an image is examined and a single determination is made, such as whether it's like a daytime picture or versus a nighttime picture. And this would be an example of a one-to-one mapping. We also have image captioning, where an image is automatically given a caption based on whatever is being shown. So this could include complex actions such as, a fox jumping over a dog. And, this task requires a one-to-many recurrent neural network where the input is a single image and the output is a phase of a phrase consisting of several words. Then we also have time series prediction, which is what a recurrent network is able to do. So different things like forecasting stock price given a history of values. This task requires a many-to-one recurrent neural network where many previous stock prices are used to predict a single future price. Then we have automatic language translation. So basically this is when you have written text or spoken words of one language, and that serves in as input to the recurrent neural network, and basically a different language representing the same text is outputted. So things like Google Translate would be a good example of this. Then we have natural language processing, which is like sentiment analysis in social media posts. So depending on the complexity of the sentiment, this recurrent neural network may be of type many-to-one or many-to-many. So if, for example, the sentiment is positive or negative, then there's only a single output. However, if the sentiment is more complex and combined with additional modifiers such as things like a positive and funny post or a negative and angry or a negative and funny, then that would be more suitable for a many-to-many implementation. Then we have text classification and sentence completion. So an RNN is used broadly in text classification, outperforming different algorithms like the support vector machine or SVM. And then we also have the segmented handwriting recognition and speech recognition app system, which have been successfully implemented using recurrent neural networks. So what I just stated was the different types of applications of recurrent neural networks, and a little bit of a brief overview of the architecture and overview of it, just as a reminder. So now that we have that, let's go over the architecture and overview of a CNN and how the RNN and CNN compare to each other and how they're similar and how they differ in different applications, or which ones do better, or which one does better using what. So that's it. Let's move on. So now let's look at the CNN architecture and framework overview. So the next important innovation in neural networks is the framework of the CNN, which is convolutional neural networks. The defining feature of a CNN is that it performs convolutional operations in certain layers, which is why it's called convolutional neural networks. The architecture slightly varies from a traditional neural network, starting with the makeup of individual layers. So, in CNNs, the first layer is always a convolutional layer. These are defined using 3 spatial dimensions: length, width, and depth. These layers are not fully connected, meaning that not all the neurons from one layer do not connect to each and every neuron in the following layer. The output of the final convolution is the input to the first fully connected layer. So mathematically speaking, a convolution is a grouping function that takes place between 2 matrices, and it combines 2 functions to make a third, thereby merging information together. In practice, they are thought of as a filter or a mechanism for feature selection. A single layer may be responsible for pinpointing very bright pixels in an image. A single layer may be responsible for pinpointing very bright pixels in an image, and a subsequent layer recognizes that these highlights taken together represent the edge of an object in an image. In addition to the convolutional layers, it is common to add pooling layers in between them. So a pooling layer is responsible for simplifying the data by reducing its dimensionality. This effectively shortens the time required for training, and it helps curb the problem of overfitting. After the convolution and pooling layers come the fully connected layers. So that's the last layer in your convolutional neural network, and you'll see in the image of this as well. In the final fully connected layers, every neuron in the first is connected to every neuron in the next. The process during this stage looks at what features most accurately describe the specific classes, and the result is the single vector of probabilities as organized according to the depth. For example, in a vehicle recognition system, there are numerous features to consider. A side view picture of a car may only show 2 wheels, but taken in isolation, this incomplete description will potentially match a motorcycle, So there will be a non-zero probability of a small car being classified as a motorcycle, or vice versa. Importantly, additional features such as the presence of windows or doors to help accurately determine the vehicle type are very important. And the output layer generates the probabilities that correspond to each class, with the highest probability is assumed to be the best choice, obviously. So in this example of identifying a car, a motorcycle would have a lower probability because there are no visible doors, obviously, when you have an image of a car. But you have to take into account all those different features in that image. So now that you have an idea of the framework of a convolutional neural network, let's go into the different applications of it. And you'll notice that some of the applications between a CNN and RNN overlap at times. So let's get to it. So let's go through the usages of a CNN or a convolutional neural network. So the most common applications for CNN is, in general, a field for computer vision. So Some of these examples include things like doing a medical image analysis, image recognition, face detection, and recognition systems, and full motion video analysis. One such system is a AlexNet, which is basically a CNN that gained attention when it won the 2012 ImageNet Large Scale Visual Recognition Challenge. It is a CNN that consists of 8 layers, where the first 5 are convolutional layers and the final 3 are fully connected layers. Then we have other applications. So you'll notice that some of them overlap with a recurrent neural network. So a CNN is able to do natural language processing, image recognition, and image analysis. So the CNN has been subject to research and testing for other tasks, and it's been effective in solving traditional natural language processing tasks. So specifically achieved very impressive results in semantic parsing, sentence modeling, and search query retrieval. CNNs have also employed in the field of drug discovery. So the AtomNet is a deep neural network that trains on 3D representations of chemical interactions, and it discovers chemical features, and has been very useful to predict novel biomolecules for combating disease. Finally, it's also worth noting that CNNs have been applied to more traditional machine learning problems, such as playing games. So both checkers and Go are games in which the CNN has been able to learn and play at a professional level. So those are just some of the different usages and applications of a CNN. So let's talk about now how they compare with each other. All right, so since we talked about the different usages of both RNNs and CNNs, let's talk about, some of the different functions or how they compare with each other. So CNNs and RNNs are not mutually exclusive. So what I mean by that is that they both perform the same functions like image classification and text classification. So at first glance, it may seem that they handle different types of problems, but it's important to note that some types of data can be processed by either architecture. So, like I said, examples like this are image classification and text classification, where both systems have been very effective in those fields. They also may benefit from the combination of these two architectures together. So this is the Dan-Q architecture. So suppose that data being modeled, whether representative of an image or otherwise temporal properties, this is an ideal situation for the merging of these techniques. One such hybrid that uses both an RNN and CNN is Dan-Q architecture. It takes in a fixed length of DNA sequence as input and predicts the properties of the DNA. The convolutional layer discovers sequence morphs, which are short recurring patterns that are presumed to have biological function. The recurrent layer is responsible for capturing long-term relationships or dependencies between these morphs. These allow the system to learn the DNA's grammar and consequently improve prediction. So, in the image, it's you'll notice that it contains both a convolutional max pooling and recurrent network with a dense layer with a multitask output. This is the architecture of a Dan-Q model, and it was built upon the deep C model, which performs the same function as Dan-Q, but does not include a recurrent neural network component. This model performs very successfully by highlighting the significance of adding memory and a feedback loop to the architecture. It benefits by considering only the more abstract data, and then it is filtered by the CNN, making the long-term relationships easier to discover. So, so now let's go to the final conclusions of how the recurrent neural network and the convolutional network compare to each other. So it goes without question that when you compare the RNN and the CNN, they both have a common place in the field of deep learning. Each architecture has its advantages and disadvantages, depending on the type of data that you want to try to model. So when choosing a framework over one or the other, or alternatively creating a hybrid approach, the type of data that you have and the job at hand are the most important points to consider. So let's just go over an overview of which ones perform better doing a different task. So an RNN is used for cases when data contains temporal properties such as a time series. Similarly, where the data is context sensitive, as in the case of a sentence completion, the function of memory provided by the feedback loops is critical for adequate performance. In addition, so the CNN is a top choice for image classification and more generally computer vision. In addition, CNNs have been used for myriad tasks and outperform other machine learning algorithms in some domains. CNNs are not, however, capable of handling a variable length input, or like a long length input. So, finally, a hybrid approach of a RNN and CNN can be superior when the data is suitable for a CNN, but has temporal characteristics that can be exploited by the recurrent neural network component. So that is the comparison between recurrent neural networks and convolutional networks.
We will now go into a question and answer portion of this video. This section is designed to test your knowledge on recurrent neural networks. Feel free to go back through this presentation to find the answer to any questions. After each question is stated, pause the video and take some time to answer it yourself. After a brief pause, we will answer each question. The first question is what kind of attention is shown on the screen? Please pause the video and take some time to answer this question yourself. If you're feeling stuck, look back on the previous PowerPoint slides to the section about attention to find the answer. The answer to the first question is additive attention. You know this is additive attention because the elements were added together, unlike multiplicative attention in which the elements are multiplied. This answer was shown in the attention section of this presentation. The second question is, how is a long short-term memory different than a gated recurrent unit? Please pause the video and take some time to answer this question yourself. How is an LSTM different than a GRU? The main difference between a GRU and an LSTM is that a GRU has two gates, the reset gate and the update gate, but an LSTM has three gates, the input gate, the output gate, and the forget gate. The GRU combines the input and forget gates into a single gate, the reset gate. A GRU is more computationally effective than an LSTM, but doesn't do as well on data using longer sequences. Additionally, LSTMs are typically more accurate than GRUs. GRUs are a much newer construction, but they have been gaining traction over their past few years of use. Picking whether to use an LSTM or a GRU is very situation specific, but LSTMs are more commonly seen over GRUs. If you did not know this answer, please review the section on LSTMs and GRUs. The third question is, what is self-attention? And how is it different from additive and multiplicative attention? Please take some time to pause the video and answer this question yourself. What is self-attention, and how is it different from additive and multiplicative attention? Additive and multiplicative attention calculate attention scores at every step taken by the decoder. They both then compare the weights to a target vector. In general, the performance of multiplicative and additive attention functions are similar, but the multiplicative function is faster and more space efficient. Self-attention also calculates the attention scores at every step taken by the decoder. However, self-attention models compare the weights to the input sequence they just saw, showing the relation within a sequence. Self-attention models only look at their own input rather than additive and multiplicative attention, which rely on input weight vectors. These three kinds of attention are all useful in different scenarios. If you did not know this answer, please review the attention section of this video. The next question is, you want to analyze time series data. Should you use an RNN or a CNN? Take some time to pause this video and answer this question. You want to analyze time series data. Should you use an RNN or a CNN? This information was presented in the lecture. If you don't know the answer to this question, I suggest reviewing the section on RNNs versus CNNs before listening to this answer. For time series data, an RNN is the better option. CNNs are mostly focused on image classification and would not be able to take in the context of the time series. Linearly sequential data would be lost in this model. Therefore, an RNN would be the better choice over a CNN when talking about time series data. If you did not know the answer to this question, please go back through this lecture and review before moving on to the next question. The final question is a conceptual question. You are given a dataset containing the script of the B movie. You want to train a model to rewrite the movie. Why would an RNN be useful for this task? Design an RNN. Please take some time to pause this video and answer this question on your own. You are given a dataset containing the script of the B movie. You want to train a model to rewrite the movie. Why would an RNN be useful for this task? Design an RNN. An RNN is the perfect model to use in this situation. As we discussed earlier in this lecture, RNNs work very well for sequential data, and text prediction is a specialty of the RNN. RNN models include special handlers for text, which include an embedding layer to convey information about the text. This was also mentioned earlier in the lecture. The embedding layer maps each word to a 100-dimensional vector. This vector supplies pre-trained weights, which are used to determine more information on the word inputted into the vector. The actual design of the RNN model is quite simple. The hardest part of the design and setup is getting the data in the correct shape for the model to handle. This process is called data cleaning. It tends to be very time-consuming and can sometimes even take more time than setting up the model itself. This topic won't be covered in this lecture. We will now go into the specifics of the design for this particular RNN. RNNs, like any other neural network, can be very customized to your task. For this particular example, we chose a very simple layout of an RNN to use. This RNN includes an embedding layer, an LSTM, and a dense layer which maps to output. These are the only layers present in this RNN. But you can add as many layers as you would like and that seem fit to solve the problem. This table shows the model summary. It lists the 3 layers that the model includes, the shape each of these layers expects to take, and the number of parameters in each layer. Another interesting feature of this table is that the total number of parameters in the model is shown. You can see, even for a very small 3-layer model, it has over 1 million parameters. This may seem computationally expensive, but with the wonders of modern computers, this calculation takes very little time. As discussed, this is a very simple RNN model. If you're looking for a more in-depth model, we do have an example earlier in this presentation which you can go back and research more. The internet also includes plentiful resources and lots of great examples on RNNs. This model is created using the sequential API. The difference between the sequential and functional APIs was mentioned earlier in this presentation. A sequential model starts with a base layer and adds more layers on top. This model is sequential. Our first layer is an embedding layer. As discussed, the embedding layer maps each word to a word vector that shows word associations and includes input weight matrix. The word count variable is simply the number of unique words in the vocabulary of our script. The 128 is the number of nodes in this layer, and the input length is 20. The input length was decided to be 20 after checking the lengths of the lines in the RNN's input data. The script of the B movie seems to have an average sentence length of 20. In our data cleaning process, we padded sentences so that they reached 20 words, and sentences that were already greater than 20 words were cut to be short enough to create a standard input size. That is the embedding layer. We then move on to the LSTM layer. 256 is the number of nodes that this layer will have. Return sequences is a Boolean value true, which gives us more information on the sequences in the LSTM and hopefully will give us a better prediction. We then add a dense layer as our final layer. The dense layer has the same number of nodes as the word count. We decided this so that the dense layer could give a probability of each word in the vocabulary to come next. This way, the model can predict a new script using the vocabulary of the original script. We used a softmax activation function in order to create this probability matrix. We then compiled the model using a categorical cross-entropy loss. A categorical cross-entropy loss is used in this situation because it is a loss function for categorical, aka non-continuous values. Our optimizer we used was SGD. I'm not going to go into any more detail on the loss function or the optimizers, as it is out of scope for this presentation. But there are very many options for loss functions and optimizers. Each has their own pros and cons. It is good practice to spend some time looking into different loss functions and optimizers and picking one that will be best for your project and your problem. We then called model.summary, which outputs the table shown in the previous slide. The final step is calling model.fit, using the training data, the validation data, and specifying the number of epochs you would like to run, which is simply the number of times you would like the model to try its best. Ideally, as you run each epoch, the model's accuracy will increase, and the model will be able to create a sample script more easily and accurately. And that is the design of an RNN for the script of the B movie. If you did not know the answer to this question, I highly recommend going back to the implementation section of this presentation and rewatching it. But don't be discouraged. Neural networks are a hard concept to grasp. I would recommend looking into further information in order to fully understand the concept. This concludes the question and answer section of our video. These are the references that we used in our project. I highly recommend looking into these resources and others if you found this presentation interesting. Thank you for listening.